What if there were devices that could solve problems in the blink of an eye, problems so complex they would take even the fastest supercomputers billions of years to unravel? What if we had machines so powerful that they could simulate all of nature's processes and deliver answers to humanity's most profound questions, from the origins of the universe to the evolution of life itself? Welcome to the mind-bending realm of quantum computing, a field that promises to transform science, technology, and even philosophy as we know it. And now, this futuristic vision has taken one giant leap closer to reality. Scientists at the prestigious University of Oxford have reached a groundbreaking milestone in quantum research. For the first time ever, they successfully connected two quantum computers and had them solve a highly complex quantum task together. In doing so, they teleported a quantum logic gate, a critical computing operation, across a distance of 2 meters. This astonishing achievement not only marks a technical triumph but also hints at an entirely new architecture for quantum computers, modular, distributed systems that could ultimately lead to a global, quantum internet. But how exactly does this marvel of science work? Why are quantum computers considered to be the next great revolution in human technology? And what gives them their extraordinary computing power that leaves even the best classical computers in the dust? To understand quantum computing, we first need to take a step back and examine how our everyday devices function. Whether you're watching this video on a laptop, a smartphone, or a tablet, all of these devices operate using classical bits, the most basic units of digital information. A bit can be in one of two states, a 0 or a 1. These states are physically represented by tiny electric charges flowing through microscopic transistors in your computer's processor. Electricity on equals 1. Electricity off equals 0. Quantum computers, by contrast, don't use bits, they use qubits or quantum bits. Like classical bits, qubits can also represent a 0 or a 1. But here's where the magic begins: qubits can also exist in a state of superposition, meaning they can be in the 0 state, the 1 state, or both at the same time. Imagine a classical bit as a coin lying on a table, showing either heads or tails. Now imagine a qubit as a coin spinning rapidly in the air. You can't say for sure whether it's heads or tails because it's in a superimposed state of both. This unique property is the cornerstone of quantum computing's power. But it gets even better. In classical computing, the amount of information increases linearly with the number of bits. In quantum computing, it increases exponentially. 2 classical bits can represent 4 possible values, but they can only store one of those values at a time. 2 qubits, however, can represent all 4 values simultaneously. Add a third qubit, and you get 8 possible states at once. With just 300 qubits, a quantum computer can represent more values than there are atoms in the observable universe, roughly 10 to the power of 80. The secret sauce doesn't end with superposition. Qubits can also become entangled, meaning the state of one qubit is directly linked to the state of another, no matter how far apart they are. When you change the state of one qubit, the other changes instantly, faster than the speed of light. This phenomenon, which Albert Einstein famously referred to as spooky action at a distance, allows quantum computers to perform incredibly fast and complex calculations by linking qubits into highly correlated networks. So what does all this mean in practical terms? Why are researchers so excited? While we're still in the early days of quantum computing, the potential applications are staggering. One of the most promising areas is molecular simulation. Classical computers struggle to model even relatively small molecules because the quantum behavior of particles quickly becomes overwhelmingly complex. Quantum computers, by their very nature, are ideally suited for this task. They can simulate the behavior of atoms and molecules down to the quantum level, potentially leading to revolutionary breakthroughs in drug discovery, personalized medicine, and materials science. Quantum computers also hold promise in the fields of artificial intelligence, cryptography, optimization, and even climate modeling. Imagine AI systems that could learn and adapt in ways that mimic the complexity of human thought, or encryption systems that are absolutely unbreakable using conventional methods. The possibilities are almost endless. Some experts even envision quantum computers capable of simulating the entire universe, unlocking answers to mysteries we haven't even thought to ask yet. But despite all this potential, quantum computing faces some enormous challenges. Why don't we all have quantum smartphones in our pockets already? The answer lies in the delicate, almost ethereal nature of qubits. These quantum bits are extremely sensitive to their surroundings. Any tiny disturbance, from heat, light, or even electromagnetic radiation, can cause a qubit to lose its state in a phenomenon known as decoherence. To maintain stability, most quantum computers must operate in carefully controlled environments, often cooled to temperatures just above absolute zero, -273.15 degrees Celsius. Creating a single stable qubit is hard enough. Creating hundreds or thousands of them and having them work together reliably is one of the biggest technical challenges in all of science. For this reason, researchers have developed error correction strategies, such as the surface code technique used by Google's Willow quantum processor. Rather than storing information in a single physical qubit, the system distributes data across multiple physical qubits, forming a more stable logical qubit. This redundancy allows the system to recover data even if some qubits fail. Speaking of Google, let's return to that incredible claim. Their quantum processor, Willow, reportedly solved a specific task in 5 minutes that would take a classical supercomputer 10 quadrillion years. That's a 1 followed by 25 zeros. The key lies in both the number and quality of the qubits. Willow is equipped with 105 superconducting qubits, which operate by allowing electrical currents to flow in tiny loops on a special chip. These currents can be controlled using microwave radiation, enabling the qubits to be manipulated and read out. There are other ways to create qubits, too. Some researchers trap ions using magnetic and electric fields in what's known as an ion trap. These ions can then be manipulated using microwave signals to encode quantum information. But regardless of the method used, the basic limitations remain. Qubits must be incredibly isolated, operated at ultra-low temperatures, and protected from even the tiniest external disturbance. This brings us back to the exciting development from Oxford. Researchers there have demonstrated a novel way to bypass some of the scaling problems plaguing quantum computing. Their approach is to use modular quantum computers, small, relatively stable units that are connected to each other using both classical and quantum channels. Each module may contain only a handful of qubits, but by linking them together, you can build a much larger and more powerful quantum system. In their recent experiment, the Oxford team connected 2 such modules and successfully had them solve a quantum algorithm collectively. Each module contained 2 qubits made of ions, specifically, a calcium ion that acts as a circuit qubit and a strontium ion that serves as a network qubit. The strontium ions in the separate modules were connected by an optical fiber. Photons, particles of light, acted as matchmakers, creating quantum entanglement between the 2 network qubits. Once entangled, each module executed a quantum operation known as a controlled Z-gate, which flips the sign of a 1 without affecting a 0. Thanks to the entanglement, the operation was effectively teleported from one module to the other. This is known as quantum gate teleportation, and it allowed the researchers to treat the 2 separate processors as if they were a single unified quantum computer. To prove that the system was truly working, the scientists had their distributed quantum computer solve a specific task using the Grover algorithm, which is designed to find a particular item in an unsorted database. The system performed the task successfully, marking the first time that a real algorithm had been executed across multiple physically separate quantum modules with true interaction between them. This may sound like a small step, but it's a giant leap for the future of quantum computing. Distributed quantum systems could one day allow us to build machines with millions of qubits by connecting many small, manageable modules. And beyond computing, this kind of networked entanglement could lay the foundation for a quantum internet, a completely new way of transmitting information that is faster, more secure, and fundamentally different from anything we use today. Keep looking up, and stay tuned to Space Lab for your next cosmic adventure.